Okay, so we are going to start this unit by talking more formally about the exponent rules that we used yesterday with our activity. Okay, so the first one I want to talk about is called the product rule. We can also see the second half of the page, the quotient rule there. I don't care so much that you remember the names of all of these things. I care that you remember how to use them, how to apply them. Okay, so the product rule, the first exponent rule that we're going to look at, applies when we are multiplying things that have the same base. Okay, multiplying things that have the same base. So x to the third times x squared, or 2 cubed times 2 to the fifth. Okay, things that have the same base and we are multiplying. When we multiply things that have the same base, we add their exponents. That's how we combine those terms, by adding their exponents. That's also how we get that x times x is x squared, right? We add their exponents. 1 plus 1 gives us 2. So if we look at a few examples of this, we've got x cubed times x to the fourth. We are multiplying terms that have the same base, so we just add their exponents. This would be x to the seventh. And then we see, as we kind of go down the line here, we've got examples that get a little more complex, but we're applying exactly the same exponent rules, okay? One thing I want you to remember is that exponent rules are for exponents. When we have numbers, we treat them the same way that we've been treating them for years and years and years, okay? So 7 times 11 is 77. We don't change the rules when we're multiplying or dividing numbers, okay? Sometimes we get so caught up in the exponent rules that we forget about that. But I'm going to pick out my numbers and multiply them. And then in order to multiply my variables, h and h to the eighth, we're going to add their exponents. Since I don't see an exponent on this first h term, that means that it's 1. So I would have h to the ninth. 1 plus 8 gives me 9. And then our third example, again, just a little bit more added on here. We've got 2 variables instead of 1. I'm going to start with my numbers here. Negative 8 times 3, that'd be negative 24. And then I'm going to look at my x's, x to the fifth times x cubed. Add those exponents, that's x to the eighth. And then for my y's, I've got y to the fourth and y to the fourth. Since I'm multiplying them, I add their exponents, and I get y to the eighth. Questions for me on our first few examples? Another thing I see from time to time is that we get a little tripped up on the parentheses when we have part of our multiplication in parentheses. Remember, that just means that we're multiplying this stuff by this, okay? It's just multiplication. The next thing we're going to look at is the quotient rule. So product rule when we're multiplying, quotient rule when we're dividing. Okay, so that means I have things with the same base that I am dividing. So we can combine these like terms by subtracting their exponents. Okay, when we were multiplying, we added the exponents. When we're dividing, we subtract the exponents. Okay, and it doesn't matter what the base is. So for my first example here, instead of a variable, I've got negative 2 as the base for my exponent. I still treat this the same way. So the base is the same, subtract the exponent. So 14 minus 9 gives me 5. So my simplified answer here would be negative 2 to the fifth power. Later on, we'll talk about actually evaluating negative 2 to the fifth and just saying what that's equal to. But for right now, I just want to focus on those exponent rules. In our second example here, I've got y's and z's. Okay, I've got some y on the top and bottom, some z's on the top and bottom. So we're going to use that quotient rule. Okay, so for y's, I've got y to the eighth on the top, and then y, or y to the first on the bottom. So we subtract those exponents. 8 minus 1 would be 7. So I get y to the seventh here. And then our quotient rule is written as the top exponent minus the bottom exponent. That's what I see here. A little bit later on, we'll talk a little more about the next thing I'm going to say. But sometimes this always doing the top minus the bottom leads us to an extra step in our work. What I tend to do is big minus little. So big exponent minus little exponent. And then my term sticks where that bigger exponent was. Okay, so I did big exponent minus little exponent, and it sticks where the bigger exponent was. So I have y to the 7th on the top. With my z's, the bigger exponent is actually on the bottom. Now we can do top minus bottom all the time. That's okay, we can do that. But then I would get z to the negative 2nd power. We're going to talk about what that means on the next page. But as I'm simplifying, that would give me an extra step if I've got a negative exponent. So what I'm going to do here is just do big minus little. So this would be 7 minus 5. That gives me z squared, right? 7 minus 5 is 2. And then I'm going to keep it where that bigger exponent was. This is going to stick on the bottom, z squared on the bottom. And then our last example here, one thing I want you to remember, again, where we're dividing numbers, that's not an exponent rule. That is just dividing numbers, okay? So I'm not going to do 8 minus negative 4. That is not how we divide, right? Negative 4 over 8, that's negative 1/2, right? I can divide 4 out of each of those or reduce each of those by 4. So I would get negative 1 over 2. And then I apply the exponent rules to the things that have the exponents, okay? So I've got p on top and on bottom, p to the 6th and p to the 8th. I'm going to do big minus little. So 8 minus 6 is 2. So p squared on the bottom sticks where that bigger exponent was. And then same with my q. 5 minus 4, and it will stick on the bottom. So 5 minus 4 is 1. So this would just be q, or q to the 1st if you'd rather. Questions for me so far? Okay, turn the page. Couple more things we're going to look at here. Okay. When I have a power of a power, so raising powers to powers or power of a power, sometimes we see this called the power rule. There are a couple of cases that we're going to see here. One of them is if I have something with an exponent and then I raise it to another power. Okay. When I have a situation like this, we multiply those exponents. So when I have a power to another power, we multiply our exponents. Okay. So if I have something like x squared to the 3rd power, that would be x to the 6th. Power to a power, we multiply. The other thing that we'll see, and we can see in our examples down here, is we also apply this rule when I have something like this. Multiple terms being multiplied and then raised to an exponent, okay? Like what we see here and here and here. We've got multiplication and division here, okay? I want to point out that this is not the same as this. These are not the same. This is only multiplication. This has addition, okay? If I see addition or subtraction, then I need to write out those terms for as many times as it tells me to, 2 plus x, and distribute, okay? This is a distribution problem. This is not what we are talking about here. We are talking about problems that look like this, okay, where it is all multiplication. If I were to write this out, it's 2 times x squared times 2 times x squared times 2 times x squared, not an addition or subtraction sign to be seen. That's what we're talking about with this power rule, okay? If I see addition or subtraction signs, that's different, okay? And we cannot interchange them. So when I have all multiplication, or division's okay, no addition or subtraction anywhere in any of these problems, what we can do when I have multiple terms multiplied together, all to a power, we distribute that power in. And where I have powers already, we multiply. So this guy would look like x to the 5th, and then times 4. y to the 4th, because I distribute that power in. And then I've got z to the 9th times 4. When I distribute that power, I have to multiply with the exponent that's already there. So when I clean this up, we would have x to the 20th, y to the 4th, z to the 13th. Or not 13, 36, sorry. I added multiply. There we go, z to the 36. Same idea for the second one here. Distribute that power in. If I already have an exponent, we're multiplying. So this would be 3 squared a to the 2 times 2, b to the 5 times 2. So when I clean this up, 3 squared is 9. This would be a to the 4th, b to the 10th. If I've got division here, I distribute that power to everything, just like we do with multiplication. So it'll go to everything on the top and everything on the bottom. Since that whole problem is all cubed, that exponent applies to everything. For a lot of the problems that we'll see where we're using multiple exponent rules in the same problem, there's not only one correct step for most of what we're looking at. So this last example here is a great example of a problem where there are many correct first steps. The first step I'm going to take, since we're talking about this power rule, is to go ahead and distribute that power in. Okay, that's not the only correct first step. We'll talk about another way we can start this problem once we work through it. So distribute that power in. We get 2 cubed, x cubed, y to the 12. 4 times 3 is 12. On the bottom, 3 cubed, x to the 6th, 2 times 3 is 6. Y to the 6th, 2 times 3 is 6. Now we're going to combine like terms. I've got x's on top and bottom, y's on top and bottom, so we'll be subtracting some of those powers. For my numbers, I'm just going to simplify. 2 cubed is 8, 3 cubed is 27. For my x's, the bigger exponent lives on the bottom, so I know whatever I have left will stay on the bottom. 6 minus 3 is 3. For my y's, the bigger exponent lives on the top, so I know my y's will end on the top. 12 minus 6 is 6. I've combined all my like terms at this point. I cannot reduce 8 and 27. This is my only y. This is my only x. We're done. Mm-hmm.
Couldn't you distribute the exponent to 2 and then wouldn't you just subtract those exponents?
These are not the same base, right?
Oh, yeah.
So that's why I don't apply those exponent rules. Now, the other way you could have started this is to start with the quotient rule, to reduce your x's, to reduce your y's, and then distribute through that 3. That is also okay. It's okay if you simplified inside parentheses first and then did that power rule. Multiple correct ways to start these problems. The next exponent rule is my favorite exponent rule because it makes so much of our work just become 1. Okay? Anything to the 0 power is just 1. Anything to the 0 power is just 1. There is a little asterisk here. In some fields of math, physics, some of those like more math and sciencey places where those two subjects overlap, there are contexts, sometimes computer science stuff, where this rule doesn't apply to 0. So there is kind of a little asterisk here that says except in some cases 0 to the 0 power is undefined. In Algebra 2, anything to the 0 power is 1. We won't run into those cases where we're worried about 0 to the 0 power being undefined. Okay. So here's what this lets us do. If I have something like c cubed divided by c cubed, The quotient rule tells us to subtract those exponents, so we would end up with c to the 0 power. Right? 3 minus 3 is 0. Anything to the 0 power is 1. So c cubed over c cubed is just 1. I'm going to guess that many of us would look at c cubed over c cubed and say, we can reduce that, or we can cancel the c cubes. What I want you to remember, because what I see sometimes is when we cancel stuff or we reduce stuff, we want to say that it's 0. This is not 0. A number divided by itself, even if it's a variable standing in for a number, is not 0, okay? 2 divided by 2 is 1. It is not 0, okay? So that's why things to the 0 power are 1. We're looking at a thing divided by itself. That's 1. Same idea here. I've got negative 3x to the 5th over x to the 5th. If I use my exponent rules, this would give me negative 3x to the 0, right? 5 minus 5 is 0, and that is 1. So I have negative 3 times 1, which is just negative 3. For our last example here, I'm going to distribute that exponent in, and I have 5 r squared s to the 4th over r squared s to the 4th. For my r's, 2 minus 2 gives me 0. I've got r to the 0, which is 1. For my s's, 4 minus 4 would be 0. S to the 0 is 1. So I have 5 times 1 times 1, which is just 5. Questions for me so far? And then the last exponent rule I want to talk about for today is negative exponents. And we've seen these here and there just a little bit. We've seen a couple of things to the negative first power, the negative second power. When I have a negative exponent, that's telling me that I need to take the reciprocal. So if I've got x to the negative second power, that is telling me that I have 1 over x squared. If I already have 1 over something, and it's got a negative exponent, so 1 over x to the negative third, that is also telling me take the reciprocal. When I take the reciprocal, the exponent is no longer negative. If I've got multiple terms, which we'll see here in just a minute, within a quotient, within a sort of fraction setup already, so for example, something like x, y to the negative second, z to the negative third, that means that this y to the second wants to live on the bottom, this z to the negative third wants to live on the top. So I move those guys to the other part of the fraction. Once I move them, the exponents are not negative anymore because they're where they want to be. Before we start working on our practice problems here, I want to point out again that these are rules that apply to exponents. If I have negative 2 over x, that is not telling me to move the 2 to the bottom. That is not what a negative number is, okay? So this is different than this, okay? The negative is the exponent. Here it's a negative 2, just a number. Question. Like if it were this to a negative something? Would I still move that down and the exponent's now positive? Yep. So this would be 1 over 5x to the 4th. If, let's say, this 2 were to the negative third power, then I would have 1 over negative 2 to the third power. But notice it's the exponent that changed, not the negative 2. Does that make sense? Mm-hmm.
So when you switch it, you switch the whole x and then whatever, you just switch the exponent like that. So if it's like x to the negative second over the y, would you switch the whole x to the negative second down, or would you just switch next the negative second to y?
No, the whole, because the exponent is attached to the x, it's the x term that comes down. So this would be 1 over x squared y. that make sense? Okay. So now let's look at a couple, I guess, more examples. We've been through quite a few, just kind of talking through this rule, but that's okay. These are good questions. For our first example here, again, multiple ways I can approach this. Anytime I see a negative exponent, I like to move it. That is usually my first step if I see negative exponents, is I move it to where it wants to live. So this guy with the -3 does not want to live on top. It wants to live on the bottom. So I would probably, as my first step, rewrite this. This is theta. Treat it just like an x here. I would move this theta to the -3 down to the bottom. And then since I'm on the same level here and we're multiplying things that have the same base, we add their exponents. This would be 1 over theta to the 13th power. You could also use quotient rule here. If I'm using quotient rule, it's big minus little. So 10 minus -3 would give me 13. And then it sticks where that bigger exponent was. So it would be 1 over theta to the 13th power. It would be exactly the same. I don't like this personally as much as I prefer to move things that have negative exponents. Okay. If this is your personal preference to just use the quotient rule, then use the quotient rule. That is okay. Second example, same idea. I'm going to start this the same way. My preference is to not have to look at negative exponents. So I'm going to take this z to the -4th and move it where it wants to go. So I would have z squared times z to the 4th. And then product rule, I'm going to add up all my exponents. So 2 plus 1 plus 4, that would be z to the 7th. This is also why I said in one of our earlier examples, if I use quotient rule and always do top minus bottom, I have an extra step. So if I use quotient rule on this guy and always did top minus bottom, I would have -3 minus 10. That gives me -13 as my exponent. So then I have to move that to the bottom. So that's what I was talking about. Sometimes you get an extra step there. Mm-hmm. I could put a 1 here if I wanted to. Okay. Okay. No, that's okay. I'm glad you asked it because somebody else is thinking about it. Okay. And I remember, because this is again something that we forget sometimes when we hone in so much on those exponent rules. 1/3 is not the same thing as 3 over 1, right? This is 3. This is 1/3 of something. Very different numbers. Okay. So it is important if my stuff is going to end up on the bottom that I have that 1 placeholder there. If you prefer to put the 1 placeholder for stuff that ends up on the top, if you want it over 1, just so you remember it's in the right spot, that's fine. This is the same thing as what I had written earlier, so that's okay to do. Last example together for today. Again, I don't like to see negative exponents, so I'm going to start this by moving this guy, this y to the -6 to the bottom. Before I do anything else, I'm going to move him. And then I'm going to start combining my like terms. So for my x's, I've got top and bottom. So I'm going to take big minus little, and it's going to stick on the bottom since that's where the bigger exponent lives. So 8 minus 4 is 4. And then my y's are only on the bottom here. So I add them, right? We're multiplying, so we add. This would be y to the 11th. Since these are all on the bottom, I do need that 1 placeholder on the top. Questions for me on our exponent rules problems? For the rest of class today, I would like you to work on the practice problems that are on page 3. So practice problems on the next page. Okay, be careful. Write down your steps. Okay, don't go too fast. And then next week, we'll continue to work on some more exponent rules.